I apply on this one the same operator, so I will get date state bay, date coupled state bay. This indicated that if I operate P twice on a state, then the state will remain the same. Okay? Changed, then again the same. So from here I saw that the P double operation, now these are operators, and operators you will have to multiply as a dot, as an inner product, as a scalar product. So P square, when operates on sine, it makes no change. So P square, the eigenvalue of this operator is 1 actually. You see, P square is equal to the same wave function. P square, the same wave function. It means it is like 1 here. When P square operates, it gives you the eigenvalue 1 in the state. Clear? You know this fact. So this implies that the eigenvalue is P square equal to 1, and this is equal to plus minus 1. When you remove square from here, then if you take a plus 1 square, it is 1, or a minus 1 square, it is equal to 1. So from this I can write that psi r1 r2 is equal to plus minus psi r2 r1. Either the exchange of parameter will generate no minus here, means it will remain plus, or exchanging the coordinates may have minus here as well. When it will remain plus, like here, psi r12 is equal to psi r21, I will call such a situation as symmetric wave function. Symmetric. And when changing the coordinates generates a minus sign here, minus sign this, then I will call it anti-symmetric. This is clear? Now we will discuss symmetric and antisymmetric in detail. Okay. So I can say for the symmetric, let's say we are having a coordinate, or let's say when f of x is replaced by f of minus x function, you replace the domain of it with a minus x, and here the sign remains plus, so you call it symmetric function. Clear? Symmetric function means this sign remains plus. If you change the x to minus x and it generates a minus sign here, you will call it antisymmetric. Consider the example of e to the power x. F of x is equal to e to the power x. Now you change f of x to minus x. Then what will happen? E to the power minus x. Minus sign is not coming out of it. So it means that this f of x is a symmetric function. Clear? Even function, which we call. And when, let's say, f of x is equal to x squared, if I change x with minus x, I will have the same function. So this is also a symmetric function. And when f of x is equal to, let's say, x cube or x odd function, So odd functions are antisymmetric. If I change f of x with a minus x, what I will get? Minus x, I will get minus x cubed. And this is equal to minus f of x. So this is an antisymmetric wave function. Let's understand this thing with the help of a plot. This is a coordinate system. And let's say I'm having a peak like this, a Gaussian distribution like this. This is your plus x, this is your minus x. Now, this peak is symmetric on this side as well as this side. Means it is just a replica of it. Clear? So I say that this distribution is symmetric around the origin. This is symmetric. If I consider like this, instead of this one, if I consider like this, that here and here. Now this distribution is the same as this distribution. If it is here or it is here, the y value remains the same. Only the x value has changed. This side is actually the y value. And this side, this one is the x value. So I changed the x. Means here it is at plus x, here it is at minus x. But the y value remains the same. So this distribution, I will say, or this function, I will say it is symmetric wave function. And in the x form, you will have squared here, the Gaussian wave function. Now if it is like this, then this function is now like this. It is symmetric or antisymmetric? This is antisymmetric. When I change x to minus x, it changes y. Y will become minus. So means the minus comes out here. So such a distribution or such a function I will call antisymmetric. So now you understand functions are the wave functions. Symmetric wave functions and antisymmetric wave functions. When you were considering the triplet state, this state and this state, they are the, like both are up or both are down. This is not a coupled state, like you have just made them up and down. This one is a coupled. Look here. Up and down, plus down and up. Now here plus is there. So if you write this one early and this one later, there is no difference at all. Clear? So it is, means if I change this one down and this one up, and this one up and this one down, there is no difference at all. So I will say this state is a symmetric state. But I cannot say this for this state. What will happen? If I make this down and this up, then this up and this down, minus sign will be generated outside. So it is an antisymmetric state. So the singlet state is in antisymmetric state. Got it? Minus sign, it will generate minus sign here. Come to your wave functions. When it remains plus, it is symmetric. When it is become minus, it is antisymmetric. Got it? Now it's clear? Okay. when this is the situation, and you also study that as the square of this is 1, means it is not making any difference. So the only thing that matters is calculating the Hamiltonian. Hamiltonian will come out to be the same for both the states. Means I will say they are degenerate states. Degenerate and non-degenerate. You haven't heard this terminology. When two states share the same energy, two or more states, we will call them degenerate states. And when they share different energies, we will call them non-degenerate. So, P is commuting with H, means these two are having the same set of eigenfunctions. So, now we will solve for this an example. And that example, whatever we have done here, will clarify this. And this is the very first example in your book. This is an example, and we are going to solve this one. Now the example says, suppose we have two non-interacting particles. So you will have to focus on the wordings. We are having two particles, and the two particles are such they are non-interacting. Means they are not interacting with each other, but they are there. Where they are there, both of mass m. Mass of the two particles is the same in n infinite square well. You remember, in infinite square well we have solved one particle. Now in the same infinite square well we are having two particles. This we have done in section 2.2, the infinite square well. In chapter 2, section 2, we have done this infinite square well. And for the one particle state, sine n of x, we have 2 over a. The wave function was 2 over a square root sine n pi x over a. I am considering it in one dimension. Psi n is a function of x only. And En was equal to n square pi square h bar square by 2m a square, where a was the width of the well. Now if I look at this term, then it's a constant, and let me write this as k. Capital K is a constant. So En I can write that this is n square k. These are the equations for the one particle system. And now I will consider two particles there, such that the two particles are non-interacting. Non-interacting means they are itself different entities. So, the one particle states I have written here. These are the one particle state. Now I will write the two particle states. So the very first will be when this is case 1. And case 1 is when these particles are distinguishable particles. When these particles are distinguishable particles, then what will happen? And in case 2, we will discuss when they are indistinguishable or identical particles. So, now the total wave function will be sine n1 n2 and x1 x2. This will be equal to sine n1 x1 sine n2 x2. You remember, we have said that I can write this is R1 and R2. If I want to write R1, R2, then it will be the multiplication of the two states. I have written it here, yes, here. Sine R1, R2, now I am having x1, x2. So it will be individually sine n1, x1, sine x2. Clear? Means I can write it as a product of the individual states. So this is a product of individual states. Clear? Okay. Now, what about the energy of this system? The energy of this system will be E n1 n2, and it will be equal to n1 square k plus n2 square k. So I can write n1 square plus n2 square, and this is k. Clear? Just k taken as common, n1 square k plus n2 square k, because particle 1 will have n1 square k, particle 2 will have n2 square k, and the whole configuration and the infinite square wave will have this much energy, the addition of the two energies. Now, the ground state means the unexcited state. So the ground state will be sine 1, 1. When both the particles are in the first level, n1 and n2, means n1 is equal to 1, n2 is equal to 1. This will be the ground state. When one of them will go to the second state, then it will be the excited state. So sine 1, 1. What will happen to this one? It will be 2 over a square root sine n1 is 1 pi x over a. So I can write that this is 2 over a, and sine n sine 2 over a from 1 and 2 over a from the 2, because both are being multiplied. So 2 over a square root, 2 over a square root. So here sine 1, sine 1. n1 is 1, n2 is 1. Put here n1 means you will have to write them individually first. So it will be 2 over a sine n1 pi x1 over a multiplied with 2 over a sine n2 pi x2 over a. So 2 over a square root multiplied with 2 over a square root will become this one, and sine n1 pi, and n1 is 1, so I am not writing n1. Pi x1 over a and sine pi x2 over a. This is the ground state of the distinguishable particles. And what about the energy E11? It is equal to 2k, because 1 square plus 1 square, it is 2 and k. So the ground state energy comes out to be 2k. Now the first excited state, this is the ground state, and now the first excited state. So the first excited state is when n1 is equal to 1, and N2 is equal to 2. I will have the first excited state. This is also possible that N1 is 2 and N2 is 1. This is also first excited state. Any of the particle can go to the next level and our configuration will become excited. Clear? So, look here. What about the energies? So here, it will be E1, 2. 1 square plus 2 square. 1 plus 4, 5. We will get 5K. And if this is E21, we will again get 5K. One particle goes